It is my great pleasure to introduce to you Professor Marek Biskup from the map department of the University of California, Los Angeles. Marek Biskup is a perfect Polish name, but do not be confused. He is Czech, but he understands a bit Polish. So he holds Master of Physics from '94 from Prague, Charles University of Prague, and then the PhD in mathematics he obtained in Nijmegen, Catholic University in Nijmegen in Holland. Nijmegen. I'm sorry, Nijmegen. And then he was hired by Bill Gates, so to speak. There was a theory group in Redmond. This group worked on different things, basically on discrete mathematics and probability. It's still there? No, it's gone. It's gone. But you spent this Microsoft research 2 years and then moved to UCLA, and he's there since then, and he's a professor there. But in meantime, he was also in Czech Republic, so he holds a docent in mathematics and probability and mathematical statistics, docent in probability and mathematical statistics, and also a docent in Southern Bohemia. In 2016, he was a fellow of Institute of Mathematical Statistics. So he's a probabilist, but also mathematical physicist, working in this probability, which is it does not exist in Poland. So this is the probability of interacting particles, spins, basically statistical mechanics, rigorous statistical mechanics, phase transitions, Ising model, but also random walks in random environment. And recently, especially, is a Gaussian free field. Thank you for coming here. And this, the floor, not the Zoom, the floor is yours.
Okay, thank you very much. So maybe we should switch to the. I think we need to share. Yeah. Go here. Oh, he said there. Yeah. Okay. Okay. All right. Let me take this away. All right. Thank you very much. So it's somewhat embarrassing to see my life laid out this fast. You know, it's been a while since I've been coming to Poland to actually visit Jacek. I was still a graduate student back then. And I guess, you know, we do talk about statistical mechanics, but not so much about spin systems, but more about quasi-crystalline order. So what I have for you today is a lecture, which is, you know, I was warned that the lecture should be introductory. So I will not be giving you kind of fancy things. So for some of you, depending on your background, you might find this kind of a routine. But, you know, the idea is to sort of give you a glimpse of a particular research area that I have been involved in, but maybe other people have as well. And, you know, to, you know, maybe attract you to that area if you feel compelled to do that. Okay, how do I move like this? Right, so the topic of the lecture is extreme value theory for a particular class of problems, which are the log correlated fields or processes in general. And I see. Okay. I think you're recording from the very beginning. Yeah, I think it's okay. Yeah. So you know, the extreme value theory in its own right is an important topic, and it's usually not really taught in probability courses because it always becomes a sideline that you don't have time for. I certainly do not manage usually to cover it, and yet it's very important in all sorts of practical applications. And the other, you know, motive of this lecture is to give you sort of a glimpse, as I said, of this you know, class of problems that currently move the research in probability theory, at least the one that I'm working in. Okay, and hopefully I will sort of at least give you some idea of a couple of buzzwords that you may have heard of. So the word like scaling limit, Extrema process, branching random walk, Gaussian free field. There might be a few more. Okay. All right. So what's extreme value theory? So extreme value theory is sort of a branch between probability and statistics. The mic's working. The setting is that you start with a bunch of random variables, call them x1 through xn. There's no assumptions a priori you want to make on these. Of course, later on you will have to, but at this moment, none. And you are interested in questions such as what's the value of the absolute maximum of these random variables? Okay, so you just take the maximum. And this maximum depends on n. It, of course, depends also on the distribution of these random variables. But the first thing you might want to know is that how big is this quantity relative to n? I mean, is there some kind of a, how does the median of this random variable scale with n? Then once you have answered that, then you might want to know how does it fluctuate around that centering quantity, like around this median, for instance. So what's the size of the typical fluctuation? And if you then get all hyped up and strong, then you might actually want to try to extract its distribution, at least in the limit as n tends to infinity. So if you want to put this in some quantitative form, is that you write the distribution of this random variable in this particularly centered form, is that you subtract some sequence, some value, deterministic value an, and then you scale the random variable by some other bn. So I write it this form, and that gives you a function. And what you would like to know in general is that what's the limit? Is there a limit of this quantity and what it is? Okay, so that's sort of the basic question of extreme value theory. There are other questions, but I don't want to spoil the punchline, so I will talk about this at this moment. Okay, so here are some real life examples. So the extreme value statistics or theory is actually used in many parts of science and engineering and beyond. So you might have heard of the prediction is that there exists a maximum age that we can live for. And the way this is done is that you take a sample of all humans, you do the statistics, and then you apply the extreme value theory to actually make a sophisticated guess what would be the maximum age if such age would exist. Okay. Then, of course, you have more practical questions for all intents and purposes, as prediction of all sorts of disasters, wildfires or floods and so on. And again, you want to do it based on the current data. You want to somehow fit the the events in the future based on what you know, and making a guess which is sophisticated enough to actually work. Same about various infrastructure failures, power grids being overloaded. It's enough if the power grid is overloaded at one point, it can create collapse. So you want to know what's the maximum load on the grid. Apparently, you can also try to, same way you do it with ages, you can try to, see if there is a minimum amount of time a human can run 100 meters. And you can do extreme statistics on that, or, worry about the annual temperature maxima, which is very pertinent for our times. Okay, so I did not give you any graphs here. What I could have done is go to Wikipedia and downloaded lots of statistics data. You can do this yourself, but this is where the theory is used. Okay, so what's the theory? So the theory is that, of course, you have to make some assumptions about these random variables. And so what I'll show you basically two things that you can do, and then argue that there are things in between. Okay, and the in between is really the interest in this topic. Okay, so the first model to consider is that you assume that these random variables x1 through xn are actually independent and identically distributed. Okay, what that means, I assume that everybody has enough background in probability to know what that means. It means that the probabilities factor on product events. Okay, and so that allows you, and that's why maximum is fairly accessible in this case, that allows you the following calculation, which I want to reproduce here in case you haven't seen it. Okay, so the probability on the left here is exactly what we're interested in. So that's the probability that the maximum centered and scaled is less or equal than t. And that, because you can rewrite it as mn being less than an plus b and t, that means it's the same event as the event that all of the random variables are less than an plus b and t. And so that gives you this, this intersection. And as I said, independence means that the probabilities on such events factor into products. So you can commute the intersection signs with the probability, and you get this quantity. And then the identical distributed part means that all of these probabilities on the right are the same, so you get the nth power of this quantity. Okay, so that's the basic calculation. Okay, and then because we want the limit to be non-degenerate, there's no way that this probability can stay bounded away from 1, because if it stayed less than 1 minus epsilon, raising that to power n would give you something that decays exponentially, and you would get a 0 limit. And so if you hope to fit the ANs and BNs in such a way that the limit exists, you have to have this probability tending to 1, which means that the probability of the complementary event goes to 0. Okay, so when you write this using the complementary event, using the probability that x1 is larger than what you've prescribed it to be, to power n, you know that this probability is small, and 1 minus something small is well approximated by e to the minus small. And so you do this approximation, and that's valid, you know, approximately, but you can justify it a posteriori. And so you get e to the minus n times this probability in the exponent. And so if I want this to have a limit, then also the exponent needs to have a limit. And so this is exactly what you have to do. So you define this f and t to be the probability of the complementary event multiplied by n, and you want that to converge. Okay, and that will not converge for just any distribution because things are not that regular. But if you assume reasonable amount of regularity, and the regularity does not mean that the random variables are continuously distributed or not. It just means that there are not sort of big gaps in the distribution where the behavior would change as you increase n, then the limit will exist. Okay, so that's a very strong assumption. But once that assumption is satisfied, and that's the surprise and the kind of the upshot of the theory, is that the limiting function is essentially constrained. It can be one of 3 types. And the one of 3 types, I mean, you still have the freedom of scaling by something else than bn, by 10 times bn, and you can subtract, instead of an, you can subtract something proportional to bn. So there's still shift and scaling that you do. If you remove that shift and scaling, you really have only 3 types of limiting distributions you can get. Okay, so this is the famous Fisher-Trippett-Gnedenko theorem. So Fisher is the same Fisher in Fisher-Wright diffusion and things like that. Very, very influential statistician of the early 20th century. And even though, you know, this theorem, actually, I just gave a bunch of names down here, was a product of a concerted effort by several people, some of whom are not even listed as authors of this theorem. And you see that there's Weibull and Frechet, which also, Frechet is definitely a famous name. And okay, so essentially you have one of the 3 kinds of limiting functions. So the first line, so that's the Weibull class. So that's for the you know, so that's a function which you know increases the probability distribution increases to some quantity, and then it becomes 1. Okay, so this typically appears if you have a distribution which is bounded, the initial distribution which is bounded. The Frechet class is for the situation when you have power law tails, in which case you have kind of, you know, significant outliers in the distribution, and that creates kind of the opposite effect, is that there's a certain minimum value where the maximum will not scale below, and then, you know, then it has kind of a parallel tail above this. And then everything else falls in the Gumbel class, and the Gumbel class is kind of ubiquitous. It appears in many situations, including things like distribution of eigenvalues of random matrices and things like that. Okay, not random matrices, I shouldn't have said that, of random Schrodinger operators. Okay, so I will reproduce this. Sorry, this is very touchy. I'll reproduce this calculation in one particular example, which is the Gaussian random variable, where things are very explicit and where you will see this Gumbel appearing. Okay, so if I now make this much stronger assumption that the x1, x2, and so on are independent, identically distributed, and with distribution which is normal, so this is normal mean 0 and variance 1, then you can do, like, you know, basically a simple perturbation analysis. So first thing is that there is a very good asymptotic form of the tail of the distribution. So this is this formula in here, which tells you that the probability that x1 is larger than t for t large is asymptotic to this quantity, 1 over t to the minus t squared over 2. Okay, and then what you need to do is that, right, what we are trying to do is to say probability that n times the probability that x1 is larger than some sequence plus bnt. Okay, that has to have a limit. So first thing, you think of t being 0, and you try to fit the an here. So the natural thing is to first, kill this n term, and that's done by squaring this thing in the exponent, dividing by 2. That cancels the 2, and you get exactly the e to the minus log n, and that's going to kill the n. Okay, but then because you have this term now sitting also in this 1 over t, you need another correction that will kill that term, and that's done here. And that's only upon after you've squared it up, wrote down the cross terms and so on. So I will not, this is a calculation you do. Okay, and then everything else, all the other terms that you might want to add would not really change the results. You don't add them. And then you see that and this still leaves the bn free, but if you calculate, what you get is that you get this 1 over root 2 e to the minus square root of 2 log n bnt. So natural things to choose bn such that it cancels this term square root of 2 log n. So this is this choice. And once you do that, you readily prove that the limit is exponential. So this is the f function, and the g, which is the distribution, asymptotic distribution of the centered scaled maximum, is exponential of that. So you get the Gumbel law. Okay, so the Gumbel is very resilient in here, and you should kind of expect it generically. The other two classes are more for special cases. Okay, so this is the first model, and of course the statisticians don't stop with that. They are interested in going beyond just the maximum. The maximum sort of sets the scale, and it turns out that for the case of ID random variables, it pretty much determines all of the rest. So what you would do is that if you want to actually keep track of the second largest value, third largest value of the order statistics of these values. So the best way to do this is to actually phrase this in terms of a random measure. Okay, so what you get up here is a measure where simply I put a point mass to a point xi reduced by an and scaled by bn. Okay, so this is a measure which has total mass n. Okay, but because of the scaling, if you look at the neighborhood of the origin, you should expect sort of one point there to be the maximum and no more points to the right. So at least kind of the upper part of the real axis will contain a controlled number of points, not necessarily finite, but sorry, it's finite but not necessarily tight. I mean bounded, but it should be tight in the limit sentence. So you take this random measure, and then you want to take a limit of this random measure. Okay, and the way you take limits of random measures is that you project them, you introduce a suitable topology on the space of random measures, which is the one for of the integrals with respect to functions which are continuous, bounded, and compactly supported. And in that topology, you extract the limit distribution. Oh, and here's my first typo. Okay, I will fix this. Sorry, this is supposed to be f, where g, of course, t is e to the minus ft. Okay. Okay, so the limit distribution is what's called a Poisson point process, and Poisson point process is this kind of ideal version of this extremal. Yes.
So, sorry, I have a question. You mentioned this notion of tightness with respect to measure. Could you remind me what does it mean?
Well, okay, so tightness means the tightness of a family of random variables means that the total mass of these random variables remains confined up to an epsilon error to a compact set. Okay, and so for random measures, you could either phrase it in terms of sets in the space of measures, or you can rephrase it in terms of tightness of the integrals of these measures with against bounded continuous functions with compact support. Those turn out to be equivalent in the usual choice of things. Okay.
Okay, thank you.
Yeah, and of course, tightness is the prerequisite for convergence in distribution. Any sequence of random variables which converges in law is tight, and without tightness, you will not have convergence. All right, so what's the Poisson point process with a given intensity? So intensity mu in this case is a measure, it's a deterministic measure at this moment. Okay, so what you do if mu is actually a probability, so the way you sample this process is very simple, is you take a Poisson random variable with parameter 1, and then you take as many samples independent from measure mu. Okay, and that gives you a collection of points, and then you use these points to form a point measure like that, and that's the limiting object. Okay, the trouble is that very often we need Poisson point process with respect to measure which is not normalized. If its total mass is 2, instead of Poisson 1, you take Poisson 2. And if the measure is in fact of infinite mass, you have to play another trick. You have to write the measure. You have to assume that it's countably, that you can split it into sum of finite, countable sum of finite measures, and then you sample of disjoint support, and then you sample each of these processes independently. Okay, so this is how Poisson point processes work, and they are usually they are very closely associated to extreme order statistics. So if you want to understand extreme order statistics, probability theory, you have to understand what Poisson point process is. That will be the first section in any book that you look at. So here is a book by De Haan and Ana Ferreira, which is a standard go-to textbook for extreme value theory. You can learn a lot from there. Okay, so the upshot here is that if I know the distribution of the maximum, the limiting distribution, I already know the distribution of the whole extremal process. Okay, you just take a Poisson. Okay, so this is model 1. Okay, so I want to move to another way to thinking of these random variables, which is very different than ID. So what I'll do is that I'll do the next natural thing is that I assume that there are some given ID random variables, y1, y2, and so on. But my random variables xk's are then partial sums of a series. Okay, so that's sums of these random variables. Well, sums of ID random variables have a name in probability. It's called a random walk. Okay, so you can think of this as a random walk. Okay, and there are sort of two typical plots you get if you try to actually simulate these random variables. If your individual random variable, the step distribution, has a finite second moment, and I'm doing these for the centered case because that's easier, then what you get something which looks like this. Whereas if the second moment diverges, you get something which looks like this, where you have these jumps. You have these kind of macroscopic jumps that remain. Okay, and then you can of course do a theory, and again it now depends on how much probability. If you've taken 2 semesters or just 1 semester, if you've taken 2 semesters, you probably know this. So there's a theorem which says that in the case on the left, which is called the CLT regime, there is in fact a way to describe the whole path of this random walk, assuming that what you have to scale the time by n. So that's what's done here. And this kind of funny expression that I have there ensures that I have a continuous function. So what you do is that you take the discrete values, you interpolate linearly between them. Okay, so that gives you a continuous function. And then you scale space by n. So you kind of smoosh everything by a factor of n in the time direction. And in the space direction, you smoosh everything by a factor of root n. Okay, and that gives you a random continuous function. And Dansker's theorem says is that under very general assumptions, so the assumption is that 0 mean, so that's the centering and the finite second moment, the distribution of this random continuous function on the space of all continuous functions on the positive real line converges to something which is known. And it's called the Wiener measure. It's the distribution of Brownian motion. And the only parameter that you have left in there is the value of the second moment, and that shows up. Oh, there's another typo. This should be 1. So this is the, or maybe I should write it like this. Oops. There should be a T. So the variance of this Brownian motion grows proportionally to the second moment of this step distribution. Okay. So if I scaled a little bit more cleverly in here, if I added this factor down here, I would have basically a unique process. Okay, so this is Dansker's theorem. this is a textbook material, so I will not talk about this. So there's a definition of Brownian motion, but if you haven't seen it, it will not help much. It's a random continuous function with given distribution, which is Gaussian, as independent centered increments, and a variance which grows like this. Okay, and what's more important for me is that this is the first example of what the current probabilists would call a scaling limit. Okay, a scaling limit is a procedure. This is not a technical term. It's a term that you use when we're talking about this over coffee. Okay, is that what you do is that you look at your problem, your family of random variables, your random object at a global scale, and then you kind of zoom out. So you keep the global scale at unit scale, and whatever microscopic details kind of become infinitesimal. Okay, and if that limit object still has a non-trivial distribution, it's not just a constant, it just doesn't get washed out, you say that we have produced a scaling limit. Okay, so this is exactly what happens here. It's because we have this random walk, which, I never told you what the scale of the step distribution was in here. I actually don't know, because it's a long time since I drew this picture. Okay, but that could be 200, it could be 2,000, it could be 200,000 steps, and it would always look the same. And that's exactly the point of this theorem. Okay, statistically, it will look the same. Okay, so why is this good for us? Because the theorem allows us to immediately extract information about the behavior of the maximum of this random walk. And that's because, just again, this is just a reminder, what is convergence in law? Convergence in law, you can define it. The way is that you need some underlying topology, and so you need to know what continuous functions are. And what you want to know is that expectations of bounded continuous functions converge. Okay, and now the topology associated with Danskir's theorem is the one which is the topology of local uniform convergence. So if I restrict attention to just a bounded interval, what I require is that two functions are closed if they're closed in supremum norm. Okay, and a maximum is of a continuous function is continuous in the supremum norm. And so I'm allowed to actually talk about the convergence of the maximum based on this theorem. And so, when I rephrase the result properly, I see that the maximum of these random variables scaled by root n, and there are n of these random variables, that converges in distribution to the maximum of Brownian motion. And by the reflection principle, you actually know that it has the law of the absolute value of the normal random variable. So this is a very different picture than what we had. When we had the IEDs, the distribution was Gumbel. Okay, there was an associated Poisson process. Whereas here, what we have is that we have the limit law is, again, it's kind of universal, and this will be true regardless of which distribution that you start from, as long as it has zero mean and second moment. And essentially all of the information is washed out except for the scale of the second moment. Okay, so what I just told you is what physicists or math physicists call universality. Universality is, again, another vague term that's being tossed around quite a lot, and that term means that you take whichever problem that you have and pass to a limit, and the limit does not really depend on any particulars that you've used. Okay, so it did not matter what random variable was the step distribution as long as it has a second moment. A modulo scaling I could even do. Okay, but still the structure of this is very different. I mean, the extremal process will not be Poisson in this case. It will actually be different. Okay, so these are kind of two extreme directions that you can look at that. I have written down what other regimes of behavior do. So essentially, once you violate the centering assumption, then things really change dramatically. So having universality does not mean that you're universal with respect to just any change. Reasonable changes are allowed, and there are some unreasonable. So changing the mean is an unreasonable change. Why? Well, because you introduce a drift to this random walk. And so for the maximum, you just need to look at a couple of initial terms, because eventually the linear asymptotics is going to take over. And so the distribution of the maximum actually converges without any scaling. Okay, so this is one change. And of course, you know, as I said, if I violate the second moment assumption, this so-called heavy-tailed regime, then under the additional assumption, a similar theorem is true, and you get a convergence to a process, which is called a stable process. And even there, you have the convergence of the maximum, but of course, you have to work a little harder to prove that. So even in this case, you have some kind of a universality, but violating the moment, the centering, you do not. Okay, so what's the punchline here? So in model 1, the maximum was carried by a single random variable. And so if I looked at the sample and went ahead and changed the random variable, I would change the maximum. In model 2, even though the maximum, you know, is achieved somewhere, if I go ahead and change one step of that distribution of the random walk, to say like resample a step of the random walk, it's not going to change the maximum by a significant amount at the limit. Okay, so the model 1, the IAD case, is determined by the individual random variables. Model 2 is determined essentially by the averages, and the individual random variables do not really play so much of a role. Okay, that's because of the structure, I assume. Okay, so the question is, and so these are kind of two extremes, and maybe some 15 years ago, physicists, Pierre Ledoussal and others, you know, have kind of wondered what happens in between, and that led to research, which, you know, there were many other inputs into this, which is now being, you know, pursued quite vigorously. So the question is, there a regime in between? Okay, and there is, and the model that you look at is what's called a branching random walk. And so I will explain what that is. So branching random walk is naturally associated with a tree.
So,
Okay,
sorry,
so,
may I have a question?
yes, go ahead.
So
anytime you can have a question, okay, yeah.
So these two different behaviors sometimes somehow corresponds to the different phases of matter. Is it right?
There is some physics that's behind there. It's really about correlations. Okay, so I didn't, you know, so I assumed IAD or sums of IADs, but you could, you know, say correlated at short distances only or correlated at long distances. And so there's a whole class of models surrounding these specific examples where you would see some similar behavior occur.
So long correlations mean something like a solid state of
matter, or
yes,
exactly, like exactly,
phase,
yeah,
yes?
exactly, yeah. So in that language, yeah. And the question is, you know, is there anything that interpolates in between?
So
okay,
kind
so
of
this
phase transition.
Whether there is a phase transition that already, you know, I mean, there is a sort of a phase transition, and it happens exactly at this logarithmic class, but I will not get to that.
Okay.
Yeah.
Okay, thank you.
But thanks, this is a good question. Okay, so the intermediate class is really carried by a variant of a random walk, which is called a branching random walk. I'm not, you know, I'm not sure. I certainly did not learn this in probability 101. So let me give you the definition. So I will have B, a number larger than 2, and an integer larger or equal than 2, which is the branching number of the tree. And the tree, you have an example of a binary tree, which is where the case B equals 2. It's just, you know, when you look at the lines of the same height, these, you can think of these as leaves of the tree above it. So the Ln is the set of vertices which are at the depth n from the root. So the root is called rho in here. So that's the L0 is the root vertex. And then Ln is this, you know, is parameterized by sequences of 1 through D of length n. And these sequences tell you how you get to that vertex as you go from the root, you know, whether you take the left or right turn. Okay, so then the tree of depth n is the union of all of these. And then you just add edges between the vertex and its ancestor. Okay, so that's the tree of, you know, but the tree structure is not so important for me. It's important to have this kind of hierarchical index. And a branching random walk is obtained similarly as the random walks. You associate with each vertex, you associate an independent random variable, make them IAD. So these are copies of a single random variable Y. And then what you do is that you go to the leaf, a particular leaf at the bottom of that tree on the right, and you go along the unique path from the root, and you add up all the random variables you see along that path. Okay, so this is the formula in here. So you first take the value at the root, and then you add up all the vertices. So this is the index which just retains the first k indices of this whole sequence sigma 1 through sigma n. So, you know, so you just go along this path maybe to here, and you add up these random variables. So of course, if I look at just one particular vertex, the law of the x at that vertex is the same as a random walk, because I'm just adding a bunch of random variables. But the difference now is that if I look at two different vertices, they will have some of the passes in common, and that's what correlates these. Okay, so this makes the vertices correlated. And in particular, it gives a lot of prominence to the values of this random walk close to the root, because the root value appears in all of these. Okay, if I change the value of y at the root, I will change all of the leaf values. Okay, so that's where the correlation is very strong. Okay, and the other thing is that there are exponentially many paths, exponentially many leaves and exponentially many paths to examine. And so even if the random variable has zero mean, I cannot expect that my maximum will stay centered or close to. So this is the branching random walk. So there's been a lot of literature on this. So what I'm giving you is kind of the result which closed the story, is by Eli Idekon from 2013. Okay, and there are some conditions you have to make. I'm not even giving you all of the conditions. I'm just giving you the essential ones. There are some tail conditions you have to satisfy. If you want to think, just think of y as a bounded random variable. Okay, but what you need to do in order to make the result kind of clean is that you need to assume that the expectation of the exponential moment of this random variable is given 1 over b. That's kind of the right centering for the exponential growth of the number of paths. And then you have another condition, which is kind of what's called the derivative martingale condition, which says that in this exponentially changed ensemble, the y has zero mean. Okay, and you can achieve these pretty easily by adding and by shifting and scaling the random variable. Okay, so this is essentially just a transformation which makes the result clean. Oh, I see I have another typo here. Minus, I apologize. Okay, and then it turns out that the maximum still has some growth in n. The linear growth that you would normally expect has been already taken care of by the first condition. And then you still have the log n growth, but with factor 3½ in here. And then there is a unadorned, so there's no further scaling. You just add t, and this converges to a quantity on the right. If I didn't have the z in there, this would be the gumbel, right? It's e to the minus t. But I have a z in there, and there's an expectation, and that's because a z is a random variable. Okay, so that's the big difference, and that's exactly what defines this class. This class has as opposed to the ordinary IAD case, it retains some global information about how these random variables are put together, how they depend on each other, and all of it's hidden in one random variable. And that random variable is the random variable z. Don't ask me what it is. We have ways to talk about them and define the random variable inherently without talking about the limit. It's a little bit like with Brownian motion, is that we have a definition of Brownian motion which does not require the theorem, but it's not much better than that. Okay, so what's the main difference is that if I work with IAD as opposed to the branching case, my z would be just a constant. Okay, in this case, it's not a constant. And the z can be thought of, therefore, as a global shift, because you can still change t by log z and transform it away and get the proper gumbel. But that just means that all of the random variables feel some kind of a global shift. And that global shift is a result of what I said, is that they all depend on the value of the root. If I change the value of the root, it's going to change it. So it has to remain random in the limit. Okay, but not more than just through one random variable. Okay, there's a little subtlety also that there's a 3/2. If you do a first moment calculation, you would think that 1/2 is the right thing. For IAD cases, you would get the half in here with the normalization that we have. Okay, but it's not a 1/2, it's a 3/2. It's a very subtle factor. It's what all of the proofs are about, but I won't tell you.
So this whole model is only dependent from one parameter, yes, b. Is all the information?
That's correct,
yes?
but also the distribution of y. And I'm fixing
Yes,
the
yes,
distribution
yes.
of y
Okay.
by these values, plus some tail conditions, which I'm not writing. Okay.
Okay, for this theorem to work, but this whole model of branching random walk is just defined on the tree where the only parameter is b, yes?
Is b and the distribution of the steps. because it's a
Okay,
sum.
okay,
It's
okay.
like for the random walk. The random walk has a step
Sure,
distribution,
sure.
and so does the branching random walk.
Sure,
Okay,
sure.
so that's also the parameter
So
of the
maybe
game.
let me put it in another way. The new information with respect to ordinary random walk is just this parameter B. Yes, it's somehow in some sense. Yes.
Well, yes. All of the Z, of course, depends on B, but it also depends on the distribution of Y.
Okay.
Right, because if I change the value of the root, I change Z, because I shift everybody by by some random constant. Okay, so as a consequence, it depends on the distribution.
Okay, thank you.
Okay, so let me move on. So soon after this, Thomas Medul proved the corresponding version for the point process. So where you look at the extreme order statistics, so you do what I said you would do for the IIDs. You take the empirical point measure, and you do the correct subtraction and scaling. So AN and BN, in this case, AN is this -3/2 log n, and BN is 1 in this case. But I wrote it this way so that you get the connection. Okay, and the limit of this also exists, and it's also Gumbel, except for the Z. So what you have is you now have a random process. And the way you sample this is that you first you pull out of your pocket, you pull a sample of Z, you condition on it, and then you use it to sample the Poisson point process. Okay, so this is a random Poisson point process. These are called Cox processes. They're standard in statistics. And so this is one example where this shows up. So again, it only changes. Essentially what happens is that you can still absorb the Z into a primary change. So the way it works is that you sample a Gumbel process, but then you shift it by log of that parameter. Okay, so that's the global effect that comes from the correlation structure. Okay, so in the whatever remaining 10 minutes or so, I want to give you kind of an overview of things that follow the same structure, so that you get some. This is more like going to the zoo, and and reading about each particular animal. I will not try to explain why things work this way. And the results are not even contemporaneous. Some of these results actually precede the results of the branching random walk. Like branching random walk has been, or was for a while, a very a challenging question, because the results existed for other situations like the branching random motion, and the trick was to actually generalize them to this structure. Okay, so the first actual mention of this is the Fisher KPP equation. Is the same Fisher. And the KPP is Kolmogorov, Petrovsky, Piskunov, 1937. So they looked at this nonlinear PDE. They had good reasons for that, which I will not go into. And essentially, it's a reaction diffusion equation. It has without the term on the right, it's just a diffusion equation. But now you have u times 1 minus u, which makes 0 and 1 attractive points of this diffusion equation, and there's some kind of a profile that appears. And there's a host of applications. You can read about this on Wikipedia. Okay, so solving this equation was a challenge, and what Fisher and KPP realized is that there's a traveling wave solution, which they didn't quite prove. But once you assume there's a traveling wave, you can actually write another equation for this, and that's why it was considered interesting. Okay, and the problem existed in the PDE literature until 1970s. That's actually quite late. Henry McKean came up with a probabilistic interpretation of the solution for a particular initial condition. So if you take the initial condition, which is the step initial condition, so it's 0 up here and 1 to the right, then the ut of x evolves in t as the probability that the branching Brownian motion, and I will define what it is has all of the particles left of x, to the left of x. So what is a branching Brownian motion? So here's a picture which I shamelessly stole from the notes of Nathaniel Berestitsky, pardon me. He doesn't know how to pronounce it properly, but we do. We always do this joke with him. So yeah, because he's French, and he says Berestitsky. So this is a sample of branching Brownian motion. So you start with one Brownian motion. So that's the path, the magenta path, or whatever is that color. And then at some random point, and that random point is governed by a Poisson point process, unit rate, you spawn another particle. And that particle starts to move as an independent Brownian motion. And then these particles, they follow the same pattern. So they keep producing offspring, and the offspring moves according to Brownian motion. Okay, and so after a while, you get this kind of mash of particles that are there, and you might be interested in the value of in the maximum particle in there, okay, which is the one which is to the top. Okay, and that's exactly what Henry McKean observed. And that led to very significant strides on this problem. So Maury Bramson, in fact, wrote his PhD thesis on this. It's a long paper, it's beautiful, on the where he essentially used this probabilistic interpretation to give full proofs of this KPP business, the traveling wave solution and so on. And then Lally and Selke observed that the limit distribution of the maximum follows the shifted Gumbel, the randomly shifted Gumbel pattern. I'm not writing this as a formula. The formula would be the same. You just need to parameterize it correctly. And then in the last decade or so, the two competing teams have figured out how to do the Extrema process. So what you do is that you, of course, shift things in such a way that your maximum particle kind of sits inside your point of view, so it doesn't move away. And then you ask, what's the particles that I see below that? Okay, and that becomes now more interesting because it's not really just the Poisson point process, because some of those particles may have been spawned just a few units of time before the maximum, before time you look. So some of those particles share the same progeny, a recent history with the maximum. Other particles do not. Okay, and so that's exactly the point, is that what you get even more interesting things. So you have this random shift, and the distribution is a Poisson point process for the local maxima, and of each of those hangs a cluster of highly correlated points, which are the ones which are your cousins and second cousins and third cousins. Okay, so it's a cluster Cox process. That's what the limit is. Okay, I'm not writing any of this because you would be, I would tire you to death for this. Okay.
Sorry.
Yes, go ahead.
One more question.
Yeah, sure.
So, in particular, from this fact that this U of Tx has this interpretation, it follows that this function is differentiable. Since
well, the initial value is not differentiable, but that's okay in diffusion world.
Oh, okay. So after some time,
yeah, but that's true.
Out,
yes.
You
can diffusion equations have this property; they smooth out everything.
Ah, I see.
Yeah. So this initial condition, that just means that your initial particle sits at 0, right? So it's the distribution of the initial particle the initial particle is forced to be at 0. So the distribution is a step function. But once you start moving, because of the diffusive nature, it becomes a smooth function, and it solves this equation.
Okay. Thank you.
Okay, so this is the branching random motion, and this was happening concurrently, sort of with the branching random walk business. Okay, so another concurrent development is something that I have been involved in. So as Jacek pointed out, I'm in Gaussian free field. So let me give you the definition of the Gaussian free field very quick. So it's a process. It's a Gaussian process. We usually make it indexed by some graph of interest. So in this case, I will take ZD. Okay. In fact, I will not even take all of ZD. I'll take a finite subset of ZD, call it lambda. Okay. And it's a process which is centered, so it has 0 mean, it's Gaussian, and the covariance structure is given by a function g lambda xy, and g lambda xy is what in probability we call the green function for the simple random walk. And that's because it solves the kind of the fundamental Poisson equation, but everything is discrete. So there's no, there are no delta functions. It's just a Kronecker delta on the right-hand side. You can also represent it as the expected number of visits by walk that started at x to y before the walk x is lambda. Okay, so that gives you a function. Now, this definition makes sense in every dimension, but dimension 2 is special. And that's why I want to, I wanted to flash this, because this is the place where the logarithmic correlations show up. I mean, they are also contained inside the branching random walk, but they're harder to justify as everything that's associated with the tree. So if there's kind of an asymptotic formula for the green function, and the asymptotic formula can be kind of concisely written as this. There's a 2 over pi. Yeah, I think it's 2 over pi. There's a constant here, 2 over pi. Yeah. Log of n over essentially the Euclidean distance between the 2 points, except that when that's 0, you just put 1. Yeah. In which example? This is for the simple random walk where you're walking on the lattice points. Yeah. Yeah. So it's the simple symmetric random walk on ZD where your steps are only unit plus or minus 1 in one of the coordinate directions. Yeah. So I'm too much used to this jargon. So true. I mean, yeah. Okay. But the fact that the green function has this form is actually kind of, again, general in 2 dimensions because it has to do with the fact that all these walks are kind of marginally recurrent. Okay. So you have this kind of logarithmic structure. So for short distances, this grows as log n. And for distances of order n, this is of order unity. Okay. So the correlations at short distances are very strong. But at global scales, they are still order unity. They're order unity, which is not very strong, but they're still non-zero. So it's not like an IID case, and that's exactly what makes this 2-dimension special. Okay. So let me, flash the. Okay, so this is just to entertain you. So on the left, you actually see the sample of this 2-dimensional Gaussian free field colored according to the height. I think this is, if I remember correctly, this is 200 by 200 box, and the span of the values is, I think, between -8 and 8 roughly. So it's not, it's pretty confined. Okay, and what you see is that you see a beautiful fractal structure. This fractal structure has been a source of much interest in probability. So in particular, Odette Schramm and Scott Sheffield in 2009 proved that you can, in a suitable way, you can think of the level lines of these functions as curves, and these curves converge again in a suitable sense to what we now call SLE4, which is a stochastic Levner or Schramm-Levner evolution with parameter 4. Yeah.
A little bit like generator for.
Maybe they can hear us in my mic.
It's look a little bit like a generator for a random terrain in computer games, something like
it's
this.
A little, yeah, it's a lot of fun. I mean, sure, it's a lot of fun drawing these pictures for sure. Okay. It's difficult to simulate GFF properly. So typically, in talks by Scott Sheffield and his company, what they'll show you the picture of an actual GFF. But once you do it on 100 by 100, it becomes just a mess because it really fluctuates quite a lot locally. Okay, and so I prefer to draw the level lines because they give you kind of a much better view of the structure. Notice that these hot points, the red ones, this is where you have very high values, or the very purple point, this is where you have the low values. Okay, and so on the right, what you see on the right is a similar. This is an actual sample of a GFF where I do not bother showing you the lattice. I just draw the values above the point. Okay, and you see that there's clustering. The data. This is not, if you draw IID data, it will be kind of very smooth. It will be a cloud. This thing clusters. Whenever the values are high, they tend to be high around it. Okay, that's all caused by depth fluctuation. Okay, so these are just pictures. This is to entertain you. So the facts that I want to share is that the problem of the maximum was solved by Jian Ding, Marek Bramson, and Ofer Zaytouni in 2015. That's published. 2013 was the first article. We competed. So Oren and I did sort of the same, but for the point process convergence. And again, it has this clustered Cox process structure. And there's a lot of conformal invariance because of the green function. It has a conformal invariant limit, and so you can use ideas from conformal invariance to actually prove a lot of things. All right, so there are 3 papers on this that we wrote. Okay, I want to show you one more example. So this example actually goes back to a paper by Erdos and Taylor from 1960, where they studied a lot of statistics of simple random walk. And one of the problems they looked at was the question is how frequently is the walk at its most frequently visited vertex? So you take a simple random walk in ZD, so that's the one which moves around the lattice of a given time length, and the time length can be defined a number of ways. You can take just the actual time length, or you can make it go until it exits from a domain. Okay, and then you ask what's the point where what's the time it spent at a point where it spent most time. Okay, and so what I'm drawing here, I'm not sure, it kind of shows a little hard to parse. So on the left, what you see is a sample random walk, as you projected the points visited. So it starts in the middle of the square and it exits at one of the points on the right. I forget which one exactly. So this is just a trace of the random walk. Okay, and then for that sample, what I drew for you is the time it spent in all these vertices. And again, this is what Erdős and Taylor pointed out. This question is particularly interested in 2 dimensions. In 3 and at 1 dimension, in 3 dimensions, you get sort of the IAD type of scaling. In 1 dimension, you get sort of in 1 dimension, the local time actually has a limit. This is the local time problem of Paul-Levy. There's a local time of Brownlee motion, so you have a scaling limit. So somehow these 2 extremes, 3 and 1 dimensions, are settled. The question is what happens in 2 dimensions. Okay. And we have some partial information on this already. So Erdős and Taylor, kind of outlined this problem and made a conjecture, which was proved in a very influential paper by Amir Dembo, Yuval Perez de Rosen, and Ofer Zaytoun in 2001. And that sort of spawned more research, and of which I would mention recent work of Antoine Joge, who actually put out, made very, constructed what the limiting process should be, and made a very significant conjecture in here. And with Oren, we've actually verified or proved this kind of, independently of his work, we proved it, but for a different setting, which is the random walk on a binary tree, which has a similar structure, but it's easier to. But this is still open. I mean, the question is, what's the distribution of the maximum time? That's open. Okay, and there are other questions, related to random walk, which actually go back to his papers, the cover time and so on, but I won't get into that. Okay, so I will just close this by, giving you what the takeaway message is here, is that there is a universality class of log-correlated processes. As I was snooping around the Wikipedia page, I noticed that somebody actually did put it on Wikipedia for the extreme order problems. So it now shows up as a line in Wikipedia. So hopefully that line will become a paragraph eventually. So, so we're trying to understand the class of problems with this type of statistics. I may have simplified it in your view too much. It requires a lot of work. Usually these papers are kind of heavy. So we do not have a uniform approach to all of these models. For each of them, we develop a specific approach, which usually requires, good insight into the problem. But still, it's clearly a universality class. They are somewhat ubiquitous in nature. It depends on your point of view. If the size of an object is proportional to my interest in it, they are ubiquitous. It's you might easily overlook that as we have. So it depends on your point of view. But they do show up in a number of cases, and these cases are what's interesting in probability these days. Okay, and the randomly shifted Gumbel law is the law that shows up universality in there, and we have some idea why this is true, why this is the universal law, but we don't have any kind of systematic proof like we have, say, for the ID case. Okay, thank you very much.
Marek? Are there any questions? Okay, go ahead.
So if I can ask one more question. At some moment, I believe it was on the 7th slide, mentions random Schrödinger operator. So I would like to ask, what exactly did you mean by this?
Right. So so I said that the Gumbel distribution shows up in even in correlated objects like spectra of operators. So if you look at the random Schrödinger operators in a localized regime. So localized means that your spectrum is actually a pure point. Okay, so then of course what it means is that your wave functions are kind of they most of the mass is concentrated in a few lattice sites if you do the lattice version of this problem, which means that if I look at 2 different eigenvalues, they're kind of almost independent of each other. And as a result of that, the eigenvalue distribution, which in all of these models you assume continuity, it usually follows the Gumbel law.
Okay, but everything is discretized, yes?
Well,
sits on the
yeah, the
lattice,
underlying
or?
lattice is discretized, but that's not so important in terms of what you expect the result to be. It's important in terms of technique.
Yes, but what I meant usually when somebody is speaking about this Schrödinger operator, I have in mind some unbounded operator in L2 space. So it is not like that here. Okay, we don't have any measure on
the operator is unbounded, but usually it's bounded from below because of the kinetic term. So you look at the bottom of the spectrum, you're looking at the and that generally has a localized part, and these eigenvalues. So so you look at the downward fluctuations, not the maximum but the minimum.
Okay.
And you look at the statistics of these points, and you should expect that you get. First thing is that you follow essentially one of the IAD classes, and because your distribution is typically bounded and smooth, you expect Gumbel.
So maybe I will put it in another way. Whenever we speak that something is random, it means that there is some measure on this space of this object. Yes.
Oh, so, I see. Maybe you're asking what it means to talk about random Schrödinger operators.
Yes, exactly.
Oh, I see. Yeah. Okay. Yeah. So random operator is a random sample from the measure space of all operators endowed with suitable topology.
Yes, but is it possible to make sense of it?
Yes.
In the general.
Yeah. Because the way you make sense out of this is that usually you have a separable Hilbert space.
Yes.
And so you evaluate how the operator acts on some core, on some class of smooth functions on which it is well defined in this Hilbert space. That's usually a separable that by assumptions that's usually a countable family. Okay. And so you essentially talk about a countable number of random variables simultaneously. And that's like talking about a sequence of random variables.
Okay. Thank you.
Yeah.
Any other questions or comments? On site here, I don't see, but online, maybe online. People are listening to us online. There are just some raise hands. No, but they can ask just without asking us for permission to ask a question. Yeah. So I guess there are no.
Okay, maybe I would have one more.
Okay, go ahead.
Sorry, but I'm a little bit afraid to ask this question, but nevertheless, let me try. So there is this whole business of non-standard analysis, which is due to Robinson. And do you think that there is some merit in trying to I don't know, use this non-standard analysis in rigorously constructing some scaling limit? I don't know whether it can give some more insight into this stuff.
I'm not the person to answer this, beyond my gut feeling, and that is that my view of non-standard analysis is that it's just a tool to make certain proofs look kind of cleaner or cooler. And so I assume that you might be able to, so for instance, a lot of these objects like the Gaussian free field, you can take a scaling limit, and even though on the lattice it's a function, that scaling limit is not a function. It's a distribution. Okay, so you all of a sudden you're forced to talk about continuum of things. You're forced to talk about kind of large sets, objects which are kind of beyond the usual counting on your fingers thing. Okay, and there it might help you, but I'm certainly not the person to to answer this with any level of insight. I would not do this myself.
Okay, I see.
But I'm already too old for that, I guess.
Thank you.
Okay.
I also have a little question.
Yeah.
So when you introduce the random walk model 2, it's on slide 9. There is a process which comes directly into my mind when I look at that. It's called the compound Poisson process, where this k, so the variable k, it's itself a random variable, namely a Poisson variable. Are there any directions into, or are there any results for compound Poisson processes which move into this direction of model 2? So what comes into my mind as well are Levy processes. So if you have a compound Poisson process, that's a special case, like Brownian motion of Levy process. So are there results in this direction?
Well, compound Poisson process, you can think kind of as a generalization of a random walk where, where the steps are not taken in discrete, but they're kind of, they kind of drop on you as raindrops, right? They come in the continuum. So certainly the equivalence of after suitable centering, you have to reduce sort of by the expectation. You should still have a class of these where you would get a CLT, like the Wiener measure type of scaling limit, and things would just go as usual. So so results are there, but they essentially start by generalizing the Donsko's theorem to this setting. And I bet there is a result like that. It's just that I don't know offhand where I would look for it. But yeah, I mean, of course, once you so in a sense, when we talked about the stable laws, when you saw these jumps, those are actually themselves compound Poisson processes. So in the regime, in the non-CLT regime, you actually do get compound Poisson process as a limit, and at least the jumps, and then you kind of suitably integrate the sizes of the jumps into a discontinuous function. And then, of course, there you won't have the CLT, but you will still have a behavior of the maximum because the process is rate continuous. So you have enough regularity to answer this question. Yeah. So the answer is yes, and it's done. It's just that I won't tell you offhand the reference to that.
Okay, I would be interested in this. Yes, thank you.
You're welcome.
Okay, I wanted to ask about this random walks on trees.
The branching random walks?
Or
you mean a random walk on a tree?
Yeah, I just wanted to ask if there is a significant, does it appear in computer science? I mean, are there any recent applications of this, I don't know, in some fields of computer science that are currently?
Again, I'm not versed in this myself. I mean, certainly, tree structures are ubiquitous in whatever arguments you do in CS, and the branching. If you mean the branching random walk, as a sum of independent random variables in there, I think that you should certainly find some reflection on that in the CS literature, even though I don't think that they will ask the same questions as we do. Okay. They might, it's a natural thing to do. And of course, the complexity of the problem is that you have an exponentially growing number of paths. So controlling all of them simultaneously, it's far more difficult than controlling just one, the sum along one path. So that's why this problem is kind of, stimulating, interesting, and different from Model 2. Model 3 really kind of captures both the local and the global structure.
Maybe I ask sort of a general question. What would be the most interesting, important problem to work in the future, attractive for, say, young people here?
I'm not gonna give that away.
Yeah, so the next one.
Yeah, okay, so I'll tell you what I'm working on right now. So I mentioned this Erdős-Taylor conjecture, or the Erdős-Taylor problem of the maximum, so I think that that's a worthwhile question, even though likely the question will be answered using specific methods which will not apply in other cases. So it means that it'll be just another case in our sleeve that we can handle. The cover time problem is very important. Maybe what I should say is that for the interest of the general audience is that there are other kind of more esoteric situations in which these statistics appear. So one of them is this, I think it's called the Keating model of the Riemann zeta function. So you can, so people have come up with statistical models of how Riemann zeta function behaves on the critical line. And apparently, and I have not, this is just, this has a value of information that you read on the internet, is that because I have not read the papers, the extreme order statistics of this function actually still follows this rule. So you can find these logarithmically correlated processes in problems which inherently have something to do with number theory, for instance. Okay, so those are the questions that you want to look into that, but then you've kind of opened up the door to wide, I think, at this moment. Yeah.
No, thank you. If there are no other questions or comments online. or on site, then we would like to thank you very much.
Thank you. We have to